But again, if we were to go on, like, let's say XR3, and we look at the same debugs, debug MPLS traffic engineering, path lookup, or debug MPLS traffic engineering, tunnel signaling. Okay, this is the equivalent of saying debug RSVP. If we go to router 1 and we shut the tunnel down, and we no shut the tunnel, if we look at XR3, what output do we get from these debugs? Okay, let's make sure we're actually logging. Let's say show log, and show log. We should be logging at level 7 to the console, which we are at debugging. But what output did it get? Didn't get any output. The reason why is that router 1, which is the head end of the tunnel, is the one that failed to do the calculation. It means it doesn't even ask the rest of the network, can you set up the tunnel to that particular destination? So again, from a troubleshooting point of view, this means that you need to start at where the tunnel is sourced from and first look at the path calculation. If I can't calculate the route to the destination, then I won't be able to signal with RSVP. And again, the way that I'd seen that on router 1 is it says the path lookup result is failed. It's not that I don't necessarily have a route to them, because if we show IP route to 3333, do show IP route to 3333, we can reach them from an IGB point of view, but the IGB table is not directly related to the TE table, because we still need to enable it either under the OSPF process or under the ISIS process. Where the fix for this should be that if we, let's parse this output again, is to add that third interface on XR3. Let's show run MPLS. This needs to say 1213, not 1212. Okay, now we can see we immediately get the output for the path signaling, and the endpoint of the tunnel is 1110, or more specifically, the head end of the tunnel is 1111. So router 1 should have gotten a log message that now path lookup is successful. If we look at the traffic engineer topology, now we see that third interface that was between XR2 and XR3 that has TE enabled. Okay, so now let's go back to what my original point of this was, where we set the admin weight of the interfaces, and assuming that we're using the TE metric for selection, which is actually should be the default, then the end path result should be that we're going to go from 1 to 2, 2 to XR2, this way, and then down. Okay, so let's bring up all of the other interfaces that I had disabled. Let's show IP interface brief, and then pipe to include admin down, which this is going to be this port here. No shut. And then on router 3, we have these two. 312. And then on the XR boxes, I believe everything is fine. Okay, so on router 3, if we look at the show IP OSPF neighbors, we should have neighbors on all 3 of our core facing links, which are these 3 here. Okay, now on router 1, let's look at let's go to the tunnel, shut it down, and we're going to do both of those debugs. We're going to debug MPLS traffic engineering path lookup, and debug MPLS traffic engineering tunnel signaling. Okay, now on the tunnel, no shut. Okay, we should see first path lookup is beginning. This should result in path lookup as success. Okay, now it says we're going to send a reservation request. Okay, reservation request is basically RSVP doing the label binding for the tunnel. So what happens is that whatever we calculated as the first hop, which in this case was router 12, we send the path message to 12, 12 sends the path message to 13, 13 sends it to 3, 3 should then reply back with a reserve message, and the label gets allocated in the reverse direction. It gets allocated from the destination back to the source. Now, if everything is successful, we should have seen that the path message comes back in from our next hop neighbor, which is this guy, 12, notify of a new label information being created. This is what tells me that RSVP is working end to end. If for some reason I send the path message out and I do not get the reservation request or the reservation reply back in, it tells me that somewhere along the path RSVP is broken. But it doesn't necessarily tell me where. So we would need to go on a hop-by-hop basis and basically look at who sent the signaling out and who did not get it back in, and that's going to narrow it down as to who either has RSVP enabled or has RSVP disabled at the port level. Okay, and now let's look at the final path. If we look at the show MPLS traffic engineering tunnels, path now goes from us to 12 to 13 and to 3, so what we wanted. Okay, if we now do a trace to 3333, we're going the path we want. Okay, now again, recall here that when I configured the tunnel restraints though, technically router 1 didn't ask for anything. This is why it was falling back to that directly connected link between 2 and 3, even though the metric was higher. Because it's basically saying on this interface, I don't have a route at all. On this interface, I have a route with a high metric. I'm going to choose the route with the high metric as opposed to choosing no route at all. Now, the other big case that you can get into here in terms of when would the tunnel not create is if you ask for a reservation that for some reason cannot be satisfied, or you ask for a constraint that cannot be satisfied. So let's say, for example, on the tunnel, that we're going to say the tunnel MPLS traffic engineering bandwidth is going to be some high value that we're requesting. Okay, so let's say we're requesting like 40 gigs of bandwidth. So 4,000 would be 4 megs, 40 megs, 400 megs, 4 gigs, 40 gigs should be 40 million. Okay, so 40 gigs of bandwidth. Okay, if we no-shut the tunnel, we should see that the line protocol does not come up. The link came up in terms of like the layer 1 status, but the protocol did not. Okay, that's an indication of either path calculation failure or of signaling failure. When we look at the show MPLS traffic engineering tunnels, it says that the path is not valid and signaling is down. Okay, this means that something was wrong in the calculation. It doesn't necessarily tell us what was wrong, but out of some of these configured parameters, either the priority, the affinity, the auto bandwidth, the required bandwidth, etc., for some reason that was not being satisfied. And actually it tells you right here what is the issue. Max interface bandwidth is not there. Okay, if we were to debug, again, MPLS traffic engineering path lookup, shut the tunnel down, and then no shut it, it should tell us here that it tells us what we are requesting, but not actually what can be satisfied. So let's look at this. Debug, MPLS traffic engineering path, let's say errors, and try this again. So path errors is not really going to tell us. What we would need to do next is basically look at what are all the attributes that are being requested and then trace that on a hop-by-hop basis to figure out who can or cannot satisfy that particular constraint. Which is why I mentioned in terms of the basic troubleshooting, one of the first things that you would want to do is to fall back to no options in terms of the constraints. So if you're not requesting bandwidth, if you're not requesting affinity, shared risk link group, the metric value, etc., then you're basically saying as long as I can form any shortest path to the particular destination, then I would be able to use the tunnel. Now, assuming that we did choose some value that is available, like let's say on the tunnel I just request, let's say 500 meg, or let's say 400 meg, because that's the same number we were using before, which is show run interface tunnel 0, do show run interface tunnel 0. We'll say not 40 gig, we'll say 400 meg. We should see that this is able to be satisfied. So path lookup was successful. Then we go into the path signaling, which is, actually I did think I'm not debugging that. Do show debug. Path lookup and errors. Okay, if we now look at the show MPLS traffic engineering topology, what we should see is that on the interfaces that we actually did the reservation on, the bandwidth is now removed from that particular portion of the pool. Now, in addition to this, when we're looking at what is the bandwidth that is available on the link, and then what is the actual allocation that the currently reserved tunnels are asking for, there's also a priority number 0 through 7 that goes along with this. Okay, what these priority values are for is two things. One is called the setup priority, and the other one is called the hold priority. Difference between them is that the setup priority says, can I start the tunnel to begin with? So I look at the topology, I look at what are all the current reservations, look at how much bandwidth is available left. If I'm able to satisfy that based on the priority number of the tunnel, based on the setup priority, then I can go ahead and do the signaling. Now, once the tunnel is actually up, there's a second priority called the hold priority. This determines, can other tunnels preempt me once I am already up? So in this example, we reserved 400 megs of the path. So assuming that we had 1 gig available on each of these quote-unquote physical ports, we reserved 400 meg, and result is that we have 600 left over. Okay, but now let's say that another tunnel later comes in, and this new tunnel wants to get 700 megs. So the system is going to say, well, what's the priority of the tunnel that's currently being configured, and then what is the priority of the new tunnel that's getting set up? If the setup priority of the new tunnel is lower than the hold priority of the existing tunnel gets torn down, and then the new tunnel is able to do its setup. So why you can see there, that's why the tunnel uses basically best effort by default, which number 7, this is the worst priority. So if I was to go to XR1, and let's now add this as a constraint. If we show run interface tunnel TE0, where right now we're not requesting any bandwidth. So we'll say interface tunnel TE0, we'll shut it down, and we'll say the bandwidth is going to be, or what? How do we specify? What is the, not to set the bandwidth of the interface, but how much do we want to reserve? Which is the, let's take a look at the command reference for this, or not the command reference, the config guide. Okay, so this was under iOS XR, and then it's under MPLS config guides and implementing traffic engineering. So let's look here for bandwidth. Not for auto bandwidth, we want to bandwidth and bandwidth pools, path option attributes. To say signal to bandwidth. Okay, signal bandwidth is, how much do we want? So let's say we want 700 megs. So that is going to be 7,000 is 7 megs, 70 megs, 700 megs. Okay, if we now no shut the tunnel and then show, let's commit. Commit. And show MPLS traffic engineering tunnels. It says the signaling is valid and the path is, or path is valid, signaling is connected. And let's see, what path are we taking? It says we're going to 12, 13, and then to 3. And if we look at this now from, let's say, 13's point of view, okay, we can see where we're debugging the signaling there, undebug all. Let's say show MPLS traffic engineering topology, and let's look at our own local identifier, 13, 13, 13, 13. And where did it get that 700 megs from? Maybe it didn't actually request it. Let's say, no route to the destination at 2. That was the last signaling error. Let's look at the Show IP route. Let's see, are we using the tunnel? It says we are using the tunnel. Let's do a trace to 3333. And it says we're going directly to router 2. So from 2, oh, 2 does have enough bandwidth available, is what it is. So right now we're going in this direction. Okay, so if we look from XR1 and look at the show MPLS traffic engineering topology for the ID 2222, it should say that it has, there we go, 700 is reserved on that link. Okay, so now let's say we're going to go over the same path, but both tunnels cannot meet the constraints both at the same time. So one of them is requesting 400, one of them is requesting 700. We're going above 1 gig, which is what is the physical bandwidth of the link. But keep in mind here, when you do these allocations, these are only reservations in the control plane. They're not reservations in the data plane. So you can commit the link and then you actually go to queue the traffic and traffic gets dropped. So it's assuming that you have some sort of like admission control at the customer ingress to make sure that they're not sending more traffic that is guaranteed based on whatever the traffic contract is. In a real MPLS design, that's always going to be the case, that the provider is always policing input, even if it's policing input to whatever the line rate is, that normally like the automation systems will have a commit that's listed on the ingress of the port. Okay, so to see if this is going to cause a problem, I'm going to shut the links down on router 2, this one and this one. Okay, so let's say on interface gig 1.213 is shut down and interface gig 1.23 is shut. Okay, now from XR1, we're going to shut the tunnel down. Tunnel TE0, shut, and no shut. Okay, if we show and commit. Do show MPLS traffic engineering, tunnels. And I think I probably needed to shut, commit, shut, commit. Okay, the tunnel now should be down. Okay, admin down. No shut, recommit. And says now the path is from us to 12 and then 12 to 3. Actually, there's another link in there that's still satisfying the bandwidth. Okay, so one more. Too many links in this topology. Gig 000.312. That needs to be disabled. Okay, so one more time. Shut the port, commit. No shut, commit. Okay, show MPLS traffic engineering tunnels. We should see now the signaling failed. Okay, now it says the path is not valid. So again, the reason why is that router 1 had a tunnel with priority 7. XR1 is also setting up a tunnel with priority 7. You can see that there are the setup and the hold priorities respectively. Since these are equal to each other, XR1 cannot trump or cannot preempt router 1's tunnel. Now, since we're specifying router 1 has one that is already up, we're comparing our setup priority to the hold priority of router 1. This means on XR1, if this value is less than that value on router 1, then this tunnel will signal and then router 1's tunnel would be torn down. Okay, so from router 1, let's look at the show IP interface brief. We should see that tunnel 0 right now is up. If we go to XR1 and we're going to change the priority value of tunnel TE0, we'll say that this guy has a priority, setup priority of 6, and we'll say a hold priority of 7. Shut, commit the changes, and let's show config fail. Says invalid or corrupt data was supplied to TE. Setup priority may not be higher than hold priority. Okay, so we need to say both are the same or this value lower than the first. So let's say priority is 6 and 6. Shut, commit. Then no shut and commit. Okay, from router 1, we should see now the path is going to go down. Okay, actually should have undebugged first. What the basic syslog message would have been is just the interface goes down. If we show IP interface brief, failed to find path to destination, tunnel is now down. But from XR1's point of view, if we show MPLS traffic engineering tunnels, its tunnels should now be up. So the same is true when you're talking about the diff-serve tunnels. The difference with the diff-serve TE is that the bandwidth value that it is reserving is coming from the sub-pool as opposed to the primary pool. Again, point of that being is that when you do prioritization of certain types of traffic, like voice or video, you cannot prioritize up to 100% of the interface. If you prioritize to about a third of the link, once you start to go beyond that, then the low latency queue starts to behave as if it was not configured. Because if a data packet comes in and a voice packet comes in, and they're both in the priority queue, effectively they're going to be first in, first out queued against each other. But the only difference would be, from a diff-serve TE point of view, is that when you request the bandwidth, you can request the bandwidth from the sub-pool. So the way that you would do that is on the tunnel interface, we say that the bandwidth is this value, but it is coming from, on tunnel 0, we say that the class type, no, not the class type, is the bandwidth is from the subpool, and then whatever particular value that you specify. The way that you allocate the subpool is on the interface that RSVP is configured on. Like here, we say the total amount of bandwidth is 1 gig, but the subpool is however much, 250 meg, for example. So now it means if someone is doing a diff-serve reservation and they request 300, even though 1 gig is available from the main pool, the subpool only has 250, and result is that the signaling is going to fail. Now, the other big one beyond this is going to be the affinity, or again, which is more commonly referred to as the link color. Now, this I would make sure that you know where this is documented, because the syntax for the affinity is not very straightforward. So in the case of regular iOS or iOS XE, this would be under path calculation and setup. So it's under MPLS configuration, path calculation and setup. And then this is going to be, I believe, the LSP attributes. And under LSP attributes, let's say affinity, which is this. So you configure an affinity value, and then you configure a mask against it to match it. So it says the mask value is the combination of which attribute should be checked. 0 means that the bit is irrelevant. If a bit in the mask is 0, an attribute value of is irrelevant. If the bit in the mask is 1, the attribute value and the required affinity of the LSP must match. So it's not a wildcard mask, it's a regular mask, like a subnet mask. So it basically means you create a number out of these affinity bits, and you map that to a color. Like 1111 is going to be color red, 2222 is going to be color blue. Then the links along the path, you assign the interfaces to have a particular affinity. Then when the tunnel requests it, if there's a match between the two of them, then the constraint is met. Now the iOS XR implementation is a little bit better than this, because you can map the affinity bits to a name, and then you just request it based on the link color, which is basically just a string that you create. So in XR, this would be under MPLS config, under traffic engineering, and then let's just search for color. Assigning color names to numeric values, which is this. So you configure an affinity map, and then you map whatever the value is to the name. Like in this case, they're saying red is 1. Then at the link level, you say the attribute of the TE tunnel is that it requires red. Then likewise at the physical interface, you say this link is red, this link is blue, green, whatever. And then if there's a match between the two of them, then the tunnel setup is correct. But really the big takeaway from this section when you're thinking about the tunnel attributes is that from a troubleshooting point of view, you always want to fall this back to the least common denominator. That if you're requesting no attributes at all, no constraints, and the tunnel is still broken, then it means it's unrelated to what you requested. Most likely in that case, it's either you forgot to enable TE under the routing process, like under OSPF or ISIS, you forgot to enable TE either globally or at the link level, or you forgot to configure RSVP at the link level. And again, this last output here, which is the show MPLS traffic engineer topology, and then pipe to include who are the identifiers and what are the addresses, that's going to tell you did TE get properly enabled on all of the interfaces. Because within the scope of the lab exam, if you get to the exam and the core is 20 routers, you're not going to have enough time to go show run on all of them to figure out where potentially is there a problem that is related to traffic engineering. And also what you can do is from the process of elimination, let's say, for example, we're going from a tunnel from 1 to 3 and we can't get it to work. Well, what you could do is say, well, let's shut down the tunnel. Let's see, can I set up from a 1 to 2? So change the tunnel destination, shut the tunnel. Change the tunnel destination to XR2, and basically on a hop-by-hop basis, see which tunnels that you can form. And then if I'm not able to create a tunnel to XR2, but I am able to create it to router 2, well, maybe that's an indication of some configuration problem on this guy. And again, the way that you can see this without even having to debug, if we show run interface tunnel 0, the minimum config of this is very straightforward. That we would say something like this: interface tunnel 1, unnumbered from the loopback, the mode is MPLS TE, the path option is dynamic, the destination is where we're going to, 12, 12, 12, 12. We shut the tunnel, and then once the config is done, we no shut it. If we no shut the tunnel and the line protocol comes up, means signaling was good. Okay, we do this again, change this to 13. Shut the tunnel, no shut it. If the line protocol comes back up again, means likewise you were able to signal to them. You may have to wait a little bit after you shut it down for it actually to go down before the process restarts, which is the problem that I had in XR there. I said shut, I made a change, no shut, and then I committed. Since the shutdown and no shutdown are part of the same commit, it doesn't actually disable the interface. You need to shut it, commit, no shut, and then recommit again. That actually causes the link to bounce. Okay, now when I bring it back up here, if the line protocol comes back again, it tells us signaling was likewise correct. Okay, if I put some garbage value in here, something that I don't know, like 1, 2, 3, 4, and now no shut, we should see the line protocol is not going to come up, which again means signaling is broken. The link will come up, but the protocol will not.